Our project was based on the idea that an electric current moving through a wire creates a temporary magnetic field. The temporary magnetic field in the wire loop interacts with the permanent magnetic field of the magnet below the loop, which then leads to the motion of the wire loop due to the interaction of the force between the two. We had to strip half the wire to act as an on and off switch. The insulated wire acted as the off switch, which disrupted the circuit, and the bare wire was the on. The magnetic field would then disappear and appear as the wire loop was rotating around through these complete and incomplete circuits. The alternating magnetic field interactions between these two types of wire caused the motion of the wire loop overall. The basis of our report was that the induced field from the batteries and through the wire loop depends on the voltage of the circuit, so we're expecting an increase in voltage to create an increase in motion at the end. Our overall research question was what factors impact the rotation speed of the magnetic motor. Our goal was to look specifically at the number of batteries and how altering the number of batteries in the circuit could create a faster motor overall. Our main finding was that increasing the number of batteries increased the rotation speed. We tested 1, 2, 3, and 4 battery circuits. However, we did have an exception to our trend. We saw that the 4-battery circuit had a lower rotation speed than we were expecting. This slide shows a variety of ways of modeling our experiment. First, we have the equations that we used. We know that force is equal to the cross product between the current vector and the B field vector, which is the magnetic field. We also know that voltage is equal to the current times the resistance. Using this, we know that the overall magnetic field is proportional to the current. We also have the circuit diagram shown with the batteries on the left-hand side. This setup shows 3 batteries, and in our overall experiment we used a number of batteries ranging from 1 to 4, with the current loop being shown in teal on the left. The diagram at the top shows the interaction of the current, which then causes an electric field, and then the B field is shown with the teal dots as it goes in and out of the page as the current circles around the loop. And the purple arrows show the magnetic field from the permanent magnet that is installed at the bottom of the loop. The interaction of these magnetic fields as the current is going through is what causes the loop to rotate overall.
Experimental setup. To get our experiment to work, we had to try multiple different things. We tried various wired loops, and we found that we put clay around our paper clips to limit interaction between the paper clips and the metal. We did 4 different trials, and one with 1 battery, one with 2 batteries, one with 3 batteries, and one with 4 batteries. To count our number of loops, we did slow motion videos. We counted in a 10-second intervals. For our data collected, we had no spinning for 1 battery. We had 61 rotations for 2 batteries. We had 107 rotations for 3 batteries, and we had 82 rotations for 4 batteries.
For our results, the 1 battery setup showed no motion but no full rotations. The setup included 4 batteries should have more rotations per second than the 3 battery setup. However, we did not observe this. Due to our equations we have previously mentioned, the rotations per second should increase with voltage. We can see that current is proportional to the magnitude of the magnetic field. As the voltage increases, the current therefore increases, resulting in a higher rate of rotations. Due to the 4 battery setup being not as expected, we investigated some possible errors that we made. Some possible errors were the wire holders did not hold the loop correctly, and the stripping the wire did not create a flipping effect, which would have caused a full circuit and then separate the circuit. The loop also was quite large and could have become unbalanced. We also did not do as many trials so we could average it. Also, in switching from our battery to the next one, we decided to do it quickly, which could have affected the result. Another issue would be that we weren't able to use a board with holders, instead use a clay paperclip setup. This would not have been able to make the loop completely flat and may have affected the magnetic field's angle. Overall, we expected a lower number of batteries to output a lower number of rotations for the recorded 10 seconds. The more batteries we added to the circuit, the larger the voltage was for a circuit, and the larger the voltage was for the circuit, the higher the current. We observed an increasing trend in the 1, 2, 3 battery setups, but the 4th battery setup was a slight decrease. This inconsistency could be due to our setup or a lack of trials. Overall, we learned that increasing the batteries increases the rotations of the motor through the interactions of the magnetic fields.